Today's lesson where we're going to be looking at space complexity. So this is more simpler than time complexity. So we're going to be brief here. So we're not going to go that deep, right, in this space complexity. So what is space complexity? Space complexity is a measure of the amount of memory an algorithm uses concerning the size of the input. So it considers the memory needed for variables, data structure, recursion stack, and other storage requirements during the execution of a program. So in this tutorial, we're going to be using this square boxes like this, right? The square bracket like this to represent the memories, to represent the memory units, right? So you can see that these two square brackets represents two memory units. This represents one memory unit usage. So that's what we're going to be using to explain this space complexity. So let's look at the first one, which is constant space complexity. So the constant space complexity, the algorithm uses a fixed amount of memory regardless of the input size. So let's give an example. Let's assume that we have a variable called this, right, array that holds a list which is 3, 44, 12, and 24, right? So here, let's say we are trying to get the value located in a particular index, and x is a variable that holds that particular value, right? So to get it, we have our array. Let's assume that I want to get the value located in index 2, right? So you can see that this is fixed because we are not iterating through these items, right? We are just going direct and fetching the value located in index 2. So this uses a fixed memory, right? This is a fixed memory unit usage. Now let's assume another example. Let's say we have a variable called n that is assigned 100, right? So this still uses a fixed memory unit, right? You can see the memory usage is constant because no additional memory depends on the size of the input. Now let's look at another example, which is a linear space complexity. Now the linear space complexity here, the algorithm uses memory proportional to the input size of n. So if n is the size of the input, the algorithm needs order of n memory for the output or temporary storage. Now let's give an example. Let's assume we have a variable called this and we have items in the list, which is this, right? So we have a total number of 1, 2, 3, 4, 5 items in the list. I want to look through for I down to the length of the array, right? So which means that I will go through 1, 2, 3, 4, 5. I will go through 5 times, which is I equal to 0, I equal to 1, I equal to 2, I equal to 3, and I equal to 4, which is 1, 2, 3, 4, 5. So I will iterate 5 times, that which means that it will consume 5 memory units. That is 1, 2, 1, 2, 3, 4, 5. 5 memory units. You can see here that if n is the size of the input, the algorithm needs order of n memory for the output or temporary storage. So even if we have an item here, if we have 6 items here, right? So for I down to this, it becomes what? I down to I trade 6 times, which means what? 6 memory units, right? So that is how the linear space works. So that is how the space complexity works. So in the average case, the worst case, and the best case, I'll work with the order of n memory units, right? So let's look at the next one, which is logarithm time complexity, right? So the memory usage grows in log time with the input size of n. Right, so let's assume we have an array like this. You can see a good example is a binary search. You can see the order of log n space is often seen in recursive algorithm like binary search, where the depth of recursion is proportional to log n. So if you have a binary search which works the sorted array, the sorted list, which is 2, 3, 5, 7, 9, 10, 13, 14, 1, 2, 3, 4, 5, 6, 7, 8. Right? So now let's assume that we have a variable called x which gets the length of the array, right? So how this works is Remember how this works is we have a total number of eight. 1, 2, 3, 4, 5, 6, 7, 8. Let's use 8, right? A total number of 8, right? So it means that 8 is assigned as 8 because we use this length of an array to get the total number of items in this list, which has 8. Now, for us to get the total memory usage, right, and logarithm time complexity is the log 2 log 2 of base 8. Sorry, log log base 2 log base 2 of 8, sorry. Log base 2 of 8. So log base 2 of 8 is 2 raised to power. Log base 2 of 8 is 2 raised to power 3. Right? So log base 2 of 8 is 2 raised to power 3. Right? Because if you do this, is you get 8 divided by 4, right? 8 divided by 2, you get what? 4. If you divide it by 2 again, you get 2, right? By 2 again, you get 1. So it's about 1, 2, 3, right? So it means that it's 2 raised to power 3, which gives you what? 2 times 2 times 2, which gives you 2 times 2 is what? 4. 4 times 2 is what? 8. So 2 raised to power 3, so it will, what the memory usage here will be 3 memory units, right? So log of base 2, when you divide it, right, so it will give you 3 memory units. So what if there are 7 items here, right? So it means that log of base 2 of 7, if you use your calculator, you will get something like this. You will get 2.8. You will get 2.8. Wait. You will get 2.8, right? You get 2.8 and some other decimal numbers here, about 2.8, right? About 2.8. So now the memory unit is discrete, right? So we'll round it up to a whole number, which becomes what? Which becomes what? 3. So it means that if there are 7 items here, it will still consume 3 memory units. Now, what if there are 16, right? So what if x is 16 items, right? It means a log of base 2 of 16 will give you what? 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. So it means that 2 raised to the power of 4 will give you what? 16, which means that the memory unit will be 4. 1, 2, 3, 4. You can see that it consumes lesser than the linear time complexity, right? It consumes lesser than the linear time complexity. It's only the constant time complexity that consumes more faster than that consume more lesser than the logarithm time complexity. So the logarithm time complexity is far more faster than linear time complexity because the linear time complexity it depends on the ON memory for the output or storage, right? So if the N is 16, that means it consumes it will be 16 memory units. If the size is 5 memory units, and so on and so forth. So in logarithm time complexity, you can see, look, when you have n is equal to 16, that means the log of base of 2 of 16, log base 2 of 16, right, which will give you 2 raised to the power 4, which therefore will be the memory units, right? So if it's 8, log of base 2 of 8, which gives you what? 2 raised to the power 3, and that 3, right? And that 3 becomes what? The memory unit, right? So that is how it works. That is how the logarithm time complexity works. So let's look at the next one, which is the linear arithmetic time complexity. Now, the memory usage is proportional to n log n, right? So, example is the merge sort requires the order of n log n memory for temporary arrays and recursive function calls. Now, let's assume that we have an array, right? We have an array like this. We have 4, we have 5, 55, we have 0 we have 1, we have 3, we have 4, we have 6, and we have 5. So 1, 2, 3, 4, 5, 6, 7, 8, right? So n takes the length of the array, right? Which means that n modes is assigned as 8, which is 1, 2, 3, 4, 5, 6, 7, 8. Now to get the total memory usage for the linear arithmetic time complexity, remember it works in the n. So the linear linear arithmetic time, okay, is space complexity, sorry. So linear arithmetic space complexity is equal to n, right? Remember it's n log n. So n times the log of base 2 of, remember it's 1, 2, 3, 4, 5, 6, 7, 8, right? N times log of base 2 of 8, which becomes our n here is 8 times, right? So our log of base 2 of 8 is what? Is 3, which becomes what? 24. So these will become the 24 memory units. So what if n is equal to 16? So what if n is equal to 16? So it becomes 8 times 4. It becomes 8 times 4, right? It becomes 8 times 4, which becomes what? 32 memory units. So what if n is equal to 7 items here? Right? Remember that if you log of to base of 2 is about 2.8 something and the memory unit is discrete, so it still maintains, it takes it down to a whole number which is 3, and it still becomes what? It still consumes for 24 memory units. You can see that logarithm time complexity consume lesser space than a linear arithmetic time complexity, right? Based on this n times log of base 2 of the n, right? Log of base 2 of the n. So that is how it works, right? So you can see that the n, if n is 8 times log of base 2 of 8, right? Remember, if n is 8 times the log of base 2 of 8. So that is how the linear mean space complexity works, right? So you can see from what we have done earlier, we can see that the constant space complexity is faster, followed by logarithm space complexity, which is consuming less space, then followed by the linear time complexity, and these followed by the linear arithmetic space complexity. So let's look at the next one, which is quadratic time space complexity. So in here, the memory usage grows proportionally to the square of the input size. So example is nested loops or operations involved in 2D arrays often have the order of n square space complexity. So let's assume that we have an array like this and we have this 45, 34. Let me use lower number, right? So let's assume that we're trying to do, okay, let me use 33 here. So let's assume that because bubble sort is a good example of the quadratic space complexity which works on big O n square, right? So one of the good example here is bubble sort. So let's, because it has a nested loop. So let's say for I down to the length of our array, right? Then for j down to the length of our array, right? It means that the I, this is 1, 2, 3, 4, right? So for the I, it means that I equal to 0, I equal to 1, I equal to 2, and I equal to 3, right? Which is 4 times. So for each of the I, which is the outer loop and this is the inner loop, so j will be equal to 0, right? J is equal to 1, j equal to 2, j equal to 3, right? So that is how it works. So j will go 4 times for each I. So you can see what happens, right? So it means that, that when n is, our n here is 1, 2, our, okay, when I, let me use I because we're using I here. So our I here is 1, 2, 3, 4. or let me use n to get of the length of our array. So the length of our array here is 1, 2, 3, 4. It means that when n is 4, right? So the memory units usage here in the quadratic space complexity, it will be 4 square. It will be 4 square, which becomes 4 times 4 will give you what, 16 memory units. So if the n is 2, is 2 square becomes 2 times 2 becomes 4 memory units. You can see the amount of memory this guy consumes, right? This quadratic space complexity consumes, right? You can see is you can see what happens, right? So you can see that the memory usage goes proportionate to the square of the input size. So if the input size, which is n, so the input size is 3, which is 3 square will give you what, 3 times 3, which is 9 memory units. And that is how this works. So let's look at the last one, which is exponential space complexity. So in exponential time space, the space requirement. Okay, in exponential time, let me do this. In exponential time complexity, the space requirement goes extremely fast as the input size n increases. So each addition step doubles the required memory. So key characteristic is now the space usage is 2 raised to power n. Is 2 raised to power It's 2 raised to the power n for every increment in n, so the space doubles, right? So this is the fastest growing complexity and quickly becomes infeasible for large n. So an example is we gave in the previous lecture we used to Havana to show example of this exponential time complexity. So here let's assume that we have n if n is equal to 4, right? So what happens is 2, right, raised to power 4, we give you what? 2 times 2, 4, 4 times 2, 8, 8 times 2, which gives you what? 2 times 2 times 2 times 2. 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, which means that it consumes 16 memory units. So if n is 5, it gives you what? If n is 5, it gives you 2 times 2 times 2 times 2 times 2. 2 times 2, 4, 4 times 2, 8, 8 times 2, 16 times 2, 32 memory units. Right, so that's why it's saying that 2 raised to the power n for every increment in n, the space doubles, right? So you can see what happens. So we have seen a good example of the space complexity where we look at the constant space complexity, we look at the linear space complexity, we look at logarithm space complexity, the linear space complexity, and the quadratic space complexity. Right, so in our next lecture, we're going to be looking at the recursion and backtracking. Right, recursion and backtracking. So thank you and God bless you. If you have any question, feel free to ask me. Right, I'm always here to answer you. Thank you. God bless you.